Any questions? Page 50. $51. Anything in there? Yeah. Question 6. 6A. Okay. All right. So we have this thing here, and we have the identity of atom Y is blah, blah, blah. Okay. Yeah, okay. So we have a mass spectrum, and I am looking at numbers ranging from 92 up to 100, and they look fairly evenly distributed, actually, between the higher and lower end. So my guess is that without doing a whole bunch of math, because wouldn't it be nice to avoid doing a whole bunch of math, that the average is going to be around 96. Yes? That's my guess. Okay? So what that means is the mass number of this element should be 96. So let's look up zirconium, molybdenum, americium, and einsteinium on our periodic table. So zirconium, I don't even know where zirconium is. Let's just look for 96, shall we? Now, the question is, are we looking for 96 at the top or at the bottom of each square? At the bottom, okay? Because the top is the atomic number, the bottom is the atomic mass. So let's look for something that's around 96. We've got 95.9, so my best bet would be molybdenum. Is that good? Okay. And you could do it with a whole bunch of math, but you can just do that approximation as well because it looks fairly evenly distributed across that entire range. Okay? Save yourself the hassle. Anything else from our mass spectra? We're good? Okay. In that case, we are going to move on to, I think we did this last, yes, we've done that and that. We're going to go to 9.3D. We're actually, I had the other class do a POGL first, but I'm going to let you guys do that towards the end to make sure I get through the same amount of stuff with you as I did with them, that we don't run out of time at the end of the day. Okay? So we are 9.3D, page 73. Although actually, no, I think it's okay. So a lot of this is going to rely on the fact that you have done most of the electron configuration POGL, which I think is true, is it not? You've done most of it? Okay. So we have these things called shells, which are also called energy levels. And each shell or energy level has an N value. So we would have N equals 1, N equals 2, N equals 3, and each one is higher in energy than the previous one. If they're higher in energy, does that mean they are closer to the nucleus or further from the nucleus? They're further from the nucleus because they would like to be closer, right? Those electrons would love to be closer, but there's no room for them in the orbitals that are closer because presumably they are filled, okay? Now, within each energy level, Okay, and this is where we get sort of into the POGL. There are one or more subshells, which are also known as sublevels. So for energy levels, we called them n equals 1, n equals 2, n equals 3. For subshells or sublevels, we don't give them a number, we give them a letter, okay? And those 4 letters are S, P, D, and F. And I believe you were introduced in the POGL to the S's and the P's, yes? So within energy level 1, okay, that's energy level 1. Our sublevels do you guys remember what kind of room there was on the first floor of that boarding house? There was a sunny room. So it was level 1, and it was a sunny room, 1S. And that is our sublevel or our subshell. There is only one sublevel, one subshell, so it's not very much of a sub at energy level 1 because there's only the 1. Okay. Now, at energy level 2, what kind of rooms did we have on energy level 2? We had sunny and pink. So we had level 2 with a sunny room. And we also had level 2 with pink rooms. Yeah? And then at n equals 3, we're going to have level 3, sunny room, level 3, pink room, and then we also introduce a new one, which I don't think you saw on the POGL. It's going to be 3, and we called them dark rooms because we were like, we needed a room and couldn't think of anything else that started with a D. Okay, we're not going to spend a lot of time talking about sunny rooms and pink rooms and those anymore because we're going to actually start looking at what those orbitals look like. Okay. So within each sublevel, within the at 1s sublevel, we have one or more orbitals. So in that level 1, how many rooms did we have? Just the 1. So if we are in an S subshell, there is only 1 orbital, okay? So we might have a 1s, we might have a 2s. That's our 1s subshell, that's our 2s subshell, just with the 1 orbital, the box representing the orbital. A p subshell contains 3 orbitals, just like how many pink rooms were there? 3. Okay, so a p subshell, we might have the 2p subshell. And how many orbitals does it have? It has 3 orbitals. And then we get into the D subshell, which has 5, and the F subshell, which has 7. Okay, so it goes up 1, 3, 5, 7, which is kind of a nice pattern, right? It's all your odd numbers, 1, 3, 5, 7. Now, how can you remember the order of these orbitals, S, P, D, F? Well, speed is fast. Okay, so S, P, D, F. Speed is fast. Forgot to underline the D, sorry. And we have 1 s orbital, 3 p orbitals, 5 d orbitals and 7 f orbitals. Now, what does that look like sort of in a more energy level focused diagram? Okay, so along the side here, this is increasing energy. And shell number 1, which is also called energy level 1, or n equals 1, it contains only one subshell, and that subshell contains only one orbital. Then when we get to energy level 2, you'll notice we have what? At n equals 2, it contains 2 subshells. The 2s and the 2p. And you know what's nice about shell 3? Guess how many subshells it contains? 3. It contains the 3s, the 3p subshell, and the 3d subshell. And if you're looking at those numbers, the 3s has 1 orbital. The 3p has how many orbitals? 3 orbitals. And the 3d has 5 orbitals. And then n equals 4, you can see I kind of ran out of room on the page. Yeah, so I put a little star so that we could continue on down below. It would be nice if we had a gigantic piece of paper, but we're not going to do that. So the 4 subshell is written separately down here. This is our shell number 4. And we have the 4s, we have 4 subshells. We have the 4s. What comes next? We have the 4. What's going to go here? 4p and the 4d and the 4f. And I'm going to write that p without the line under it because it looks like a weird f, and that's confusing me. There we go. And one thing I'd like you to notice about all the orbitals in a subshell or in a sublevel, I'm going to call it a sublevel just so you get used to hearing both terms because they are both acceptable. All the orbitals in a sublevel are at the same energy. And you'll notice that the P are at a higher energy than the S. than the 4s. 4p is higher energy than 4s. 4d is higher energy than 4p, and 4f is higher energy than 4d. And shells 5 and 6 look pretty much like shell 4. We don't go past f orbitals, and we'll see why we don't later on. Okay, we just kind of run out of elements before we would need to use a g orbital, which I think is the one that would come next, or something like that. I don't know. Okay, so those are our subshells, and now we're going to take a closer look at what they look like and a few little ways of remembering what they look like. So I don't know how much you remember of that video we watched with Schrödinger and his waves. Okay. In that, we were looking at the shapes of the orbitals in hydrogen. So an orbital is an area around the nucleus that can be occupied by electrons. Okay, so it's an area around the nucleus that can be occupied by electrons. How many electrons maximum per orbital? And remember, an orbital is like a room. How many borders could you fit in a room? Did you get to that part in the Pogo? Yes? No? 2. Yeah? 2 electrons maximum in any orbital. You can put 1 in, that's fine. You can put 2 in, that's fine, but you cannot put 3. Okay? So one room can contain only 2 people, one orbital can contain only 2 electrons. Now the letters S, P, D, F tell you the shape of that area. So they tell you the shape of the orbitals in that sublevel. So that's what the letter tells you. It tells you the shape. So in an S subshell, we only have 1 orbital, and those orbitals are spherical. Guess what? S, sphere. Yeah? That one's nice. I think that might actually be why it's called an S orbital. The other ones are not quite as nice. All right? So at energy level 1, you can see we have a sphere, and at the center of this sphere would be the nucleus. Yeah? At energy level 2, we also have an S subshell, which is made up of 1 S orbital, just the one. And then at energy level 3, we also have an S orbital. What do you notice about these as we go from energy level 1 to energy level 2 to energy level 3? They are getting bigger, okay? So what that means is that the electron density within that orbital is further from the nucleus, okay? So in the 2s, the electron density is further from the nucleus than in the 1s. And because it is further from the nucleus, that means its energy is... Does that electron want to be closer to the nucleus, or does it want to be further from the nucleus? It wants to be closer. So is it at a higher energy or at a lower energy? It's at a higher energy. Yeah? It's at that amount of energy as opposed to that amount of energy. Yeah? So 2s is at a higher potential energy than 1s. It would be the same thing for 3s compared to 2s. Yeah, I'm not going to write it all down again, but it's the same deal. Okay, so those are our s orbitals, and they occur in energy level 1, in energy level 2, in energy level 3. Every single energy level has an s subshell with that one single s orbital in it. Okay, now p orbitals are peanut shaped. Now, not like if you have like the peanuts out of the shell, these are like peanuts in the shell. And just in case you have not seen peanuts in the shell, here they are. You can see that they have like sort of a blob on one end, and then they go in the middle, and then they have a blob on the other end. Yeah? So that's the kind of peanut we're talking about. So peas are peanut shaped. We often draw them as a kind of double balloon shape. Okay? And there are 3 different orbitals, but they all have the same shape because the P tells us the shape. So we have 3 double balloon shaped orbitals. And the only thing different about these orbitals is their orientation in space. So you can see here we have, this is a PZ, and it goes along the Z-axis. We have a PX orbital, and it goes along the X-axis, and we have a PY, and it goes along the Y-axis. And so these 3 orbitals are all perpendicular to each other. Yeah, they're all at 90 degrees to each other. But one thing I want you to notice about this is that although there are 2 lobes to each orbital, those 2 lobes together just make 1 orbital. Okay? So it's not like we can, I don't know what I'm trying to say. Forget I said that. Okay. Now, what the heck is this double balloon shape? If you remember, electrons are both what? Particles and waves. So when we measure them or look at them or hit them with a photon or do something to them, they are particles. The moment we stop looking at them, we stop interfering with them, we stop doing anything with them, what do they become? Waves. And not like a wave, like in the sense like, oh, look, it's a wave, right? I'm like, oh, that's a wave. I know that's a wave. They become a wave in the sense that this double balloon shape is a wave, okay? They just sort of collapse into this blobby shape, yeah? So if I'm not looking at it, we have this blobby shape. And let's say we just start to look at it, okay? So we look at it. Where might the electron be? It could be anywhere in there, okay? And then if I look at it again, it could be somewhere else. It could be in that same lobe, or it could be in the other lobe, okay? So then I stop looking at it, it becomes a blobby shape, and then I look at it again, and oh, look, there it is. And we end up with, I don't know if you remember this from the video, we end up with a high density in the middle of the blobs, right? High density in the middle of the blobs, and a lower density towards the outside of the blobs. And eventually you hit a border where there's essentially no electron density outside of that. Yeah? I also want you to notice that at the very center, where the nucleus is, there is a node. And a node is where there is no probability of finding an electron. So there's zero probability of finding an electron in the nucleus. So far, so good? Okay. So these are our individual p orbitals. They all have the same energy. Okay, and if we were to take the p subshell all together, we would have the x, the y, and the z. This is 2 dimensions, so it doesn't look great, but you would have one going up and down. You would have one going left and right. Okay, so we would have our, let's see, up and down is z, left and right, let's call left and right x. Which way would y go? Yeah? Oh, I look like I'm making a rude gesture. But anyway, yeah, so they're all perpendicular to one another. So even though this little p subshell here does not look 3-dimensional, that's what it's supposed to represent. Okay, 2 of them, one sticking in and out of the board, one going left to right and one going up and down. Okay. Now, just because I wanted to mention this, if you have 2 electrons in here, that does not mean that one electron lives in one lobe and one lives in the other lobe. Okay, that's not how it works. Okay, if you have 2 electrons in here and you take a measurement, they might both be in different nodes, or they might both be in the lobe. They might be in the same lobe, okay? It just depends on where they happen to be. There's an equal probability for both of them, okay? While we're at talking about two electrons, how do we represent electrons? What symbol do we use? We use arrows. So we would have one that is up and one that is down. And we could also show them this way. We can use a half arrow and a half arrow. That's also a way of showing two electrons in one orbital. Whenever you have two electrons in one orbital, one has to be spinning in one direction, and the other has to be spinning in the other direction. And we call these spin up and spin down, okay? Two electrons in the same orbital must spin in opposite directions. We have spin up. Oh, what am I doing? Why did I put a number 1? I just meant to draw half an arrow. Spin up. And this is spin down. And that has to do with the fact that electrons are negative, and what do they do to each other? They repel. But if you get a charge and it's moving, what do you create? Physics people? Moving charges create magnetic fields, right? And if they're spinning in opposite directions, then you're going to have a north with a south and a north with a south. And so you'll have the north and south pole near each other, and they'll attract, and it helps stabilize them. Okay, at least that's kind of my understanding of it. You don't really need to understand any of that because this is chemistry. We'll let the physics people deal with that aspect of it, okay? But what you do need to know is that within any orbital, you have to have spin up and down. You cannot have two of them with spin up, because then it would be like having a negative beside a negative and a north pole beside a north pole and a south pole beside a south pole, and then everything's repelling, and it just doesn't happen. Yeah? Okay. Now, here's our p orbitals, peanut-shaped. D orbitals are more complicated. D orbitals are shaped like a daisy. Okay, here's our little daisies. And if you're wondering what that square is doing there, it is just showing you what plane these little things are in. And d orbitals, they're all the same energy. Okay, they only start at n equals 3. So s orbitals we have in all the time. P orbitals only start in level 2. D orbitals only start in level 3. And F orbitals only start in level 4. Okay? And remember, we have 5 of them. And to me, it made sense that my p orbitals all had the same energy because they're all the same shape and they're all the same distance from the nucleus. So does that not kind of make sense that they all have the same potential energy, right? So that made sense to me. And I'm like, they're oriented differently, but they're all the same distance from the nucleus, so they should be the same energy. And it looks like the same thing for D, but then we have this weird one at the end, the weird little love child of a z-axis and a z-axis. Okay, so we have dxy, which is in the xy plane, or sorry, dyz, which is in the yz plane, dxz, which is in the xz plane, dxy in the xy plane. We have dx squared minus y squared. I don't even know what that means. Okay, and then we have dz squared, which I don't really get either. So what you need to know about these is they are all at the same energy, even though we have one which is a completely different shape. It is still the same energy as all the others. It must work out mathematically that way. I don't know why, but there we are. Okay? And we have 5 of them. F orbitals, remember we had 1 s orbital, 3 p orbitals, 5 d orbitals. How many f orbitals do we have? 7. Okay. And they are super fancy. Okay. Or sometimes people call them flowers because they look like flowers, but I like fancy because then I can have D for Daisy. Okay. And they're just complicated, and you don't need to know what they look like, really. You can just appreciate their weirdness and be like, okay, moving on. All right? Because very soon we're going to stop talking about the shapes and just be like, okay, an s orbital looks like this. And p orbitals look like that, because I got 3 of them and they're all the same energy. You know what I mean? We're going to go to boxes very soon. Okay, and we already have a little bit. So those are the Fs. And then this is unfortunately sideways, so I'm just going to grab from block 4. I printed it this way, the right way around. There we are. Okay, so here are your orbitals, just so you can see them all in one place. Okay, so you can see that the s, we just have 1 s orbital, and they are present at n is greater than or equal to 1. We have 3 p orbitals, and they are present at n is greater than or equal to 2. We have 5 d orbitals present at n is greater than or equal to 3. And we have 7 f orbitals present at n is greater than or equal to 4. I just like this because it put them all on one page and you could kind of see them and compare them and see 1, 3, 5, 7, nice little triangle. Okay. Get back here. Now here's our energy level 1. We just have a 1s orbital. That's it. Oh, and this should say there's a typo over here. I need to fix this. The orbital is a 1s orbital, and it's not in the 2s subshell, is it? It's in the 1s subshell. Okay, so that was a typo. Please fix that one. And we are at energy level 1. At energy level 2, we have the 2s subshell, sublevel, and we have the 2p sublevel, which is made of 3 p orbitals. The 2s sublevel is made of 1s orbital. Are we getting the idea of what a shell and a subshell and an orbital are? Yeah? Okay. Because then we get to energy level 3, and we have our 3s sublevel. We have our 3p sublevel, and we also have our 3d sublevel. You should probably be familiar with px, py, pz, because that's very easy to visualize. Yes, px, py, pz. But most of the time, you're just going to call them the 3p orbitals, okay? You do not need to know dx squared, y squared, minus y squared, dxy, d blah, 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 blah. Okay, you do not need to know these little doodads down here. You can just forget about them, okay? They're complicated. I don't know what they are, whatever, okay? Is that as far as I got with my other class? I feel like it was, although we do have our little thing here. That is as far as I got with the other class. So at this point, I'm going to let you guys finish up Pogle's 9.3, what was it, B? Yeah, 9.3B and 9.1G. And if you would like to work with whatever people you would like to work with today, I'm okay with that. If you want to go back to the groups you were working with last day or the day before, you can do that. I suggest, though, that you kind of be in a group of at least 3 or 4, because then you've got all your brains, right? If you're just in a group of 2, that's kind of like, you know, better to have more brains. More brains are better. Now, if I do see you just sitting in partners, I will put you in groups. So if you would like to get yourselves please together in little groups so you can work together and have more brains, I will be happy to accommodate you, but otherwise I will forcibly move you. Okay, so go find yourself some people. Pardon me, you're done? If you're done, I will figure out what you're doing for next day. For homework, I think we are doing... This is kind of a review. 9.3C. You can watch the video for 9.3C and fill it in. So this weekend you've got some watching videos and filling things in, 9.3C and 9.3G. So if you finish all the stuff, you can work on those, okay? It's actually it's okay. So we've got here and then one mass is that's oh sorry that but we don't actually have much. Mostly what we have so together they will make yeah. This is our main process. So we have okay, and then here. Anyway, that's so what you're supposed to do that. So we're gonna have here. DR2, and it's gonna be our VR 79 plus VR. We have to add the 9. Yeah. So that's gonna be VR 8. Yeah, and then this one is gonna be VR2 60, which is 3. Oh, what was the other one? We have to watch this one here, not my face. Two. Then what was the other one? Yeah. 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 Makes sense. Yeah. Okay. Okay, well. Actually, can I get you guys to do 9.3H as well? Okay, you got a whole weekend to do it?
Wait, is H also video?
H is also a video with some filling in some exercises.
Okay. Oh, that's another thing.
So we got 3 things: 9.3C, 9.3G, 9.3H. And we'll all come back knowing how to do electron configurations, or at least mostly. And then we'll debrief on it on Monday. Okay, let's do this.
Okay.
You might even find 9.3C you don't even need as much because we've already talked about orbitals, but it could be a good review. Up to you, whatever. Okay, let's grab this.